The observable universe refers to the vast region of space that we are capable of observing, detecting, and studying using our current technology and scientific instruments. It is essentially the portion of the universe from which light, or other signals, has had enough time to reach Earth since the beginning of the universe. The observable universe is not the entirety of the universe. Rather, it is the part of the universe that is within our cosmic horizon, the maximum distance over which light can travel in the time since the Big Bang. The observable universe is constantly expanding as more light from distant objects reaches us, but there is a boundary to what we can observe. This boundary is determined by several fundamental factors, including the speed of light and the age of the universe itself. One of the most critical limitations in understanding the observable universe lies in the speed of light. Light travels at an incredibly fast speed, roughly 300 kilometers per second in a vacuum, but even at this speed, it takes time for light to travel across the vast expanse of space. The speed of light, therefore, imposes a fundamental constraint on how far we can see into space and how much of the universe we can observe. This limitation becomes particularly significant when we consider the vast distances involved in cosmic observation. When we look at distant stars, galaxies, and other cosmic phenomena, we are not seeing them as they are at the present moment. Instead, we are observing them as they were in the past, sometimes billions of years ago. For example, when we observe a galaxy that is 100 million light-years away, we are actually seeing that galaxy as it appeared 100 million years ago. The farther away an object is, the older the light we are receiving from it, and the further back in time we are looking. The speed of light, combined with the finite age of the universe, defines the boundaries of the observable universe. The universe is approximately 13.8 billion years old, and this age sets a maximum limit on the distance that light could have traveled since the Big Bang. The observable universe is thus limited to a spherical region around Earth, with a radius of approximately 46.5 billion light-years. This is because the universe has been expanding since the Big Bang, meaning that the actual distance to the farthest objects we can observe is much greater than 13.8 billion light-years. The expansion of the universe stretches space itself, which causes distant objects to recede from us, making the observable universe larger than the simple distance light can travel in 13.8 billion years. The observable universe, therefore, is a dynamic and ever-expanding region. As time passes and light from more distant objects reaches us, the observable universe grows larger, allowing us to observe farther and farther into the depths of space. However, it's important to recognize that there is a limit to how far we can observe. Objects that lie beyond this limit are not observable by any means, simply because their light has not had enough time to reach us. This boundary, known as the cosmic light horizon, marks the farthest distance from which light has had time to travel to Earth since the beginning of the universe. Beyond this horizon, we cannot observe any objects, and we are left to speculate about what might lie there. The concept of the observable universe introduces several important ideas about the nature of space and time. It reveals that our view of the cosmos is inherently limited, and this limitation is tied to the finite nature of both the speed of light and the age of the universe. As we look out into the universe, we are not simply observing a static snapshot of the cosmos. We are looking into the past, witnessing events and phenomena that occurred long ago. This dynamic, time-bound perspective adds a layer of complexity to our understanding of the universe and our place within it. This limitation of observation also has profound implications for our understanding of the universe's true size. The observable universe is just a small fraction of the entire universe, which could be vastly larger or even infinite beyond the limits of what we can observe. While the observable universe is bound by the speed of light and the age of the universe itself may extend far beyond this boundary, potentially stretching on indefinitely. The actual extent of the universe remains a mystery, and scientists continue to explore various theories about what lies beyond the observable horizon. One of the most intriguing aspects of the observable universe is that the further we look into space, the further back in time we are able to peer. For example, when we observe the cosmic microwave background CMB radiation, we are seeing a faint afterglow of the Big Bang itself, imprinted on the universe when it was just 380 years old. This radiation provides a snapshot of the universe in its infancy, offering a glimpse into the conditions that existed just after the birth of the cosmos. As we look even farther into the universe, we see galaxies and stars that formed billions of years ago, and the light from those distant objects has traveled across the vast expanses of space to reach us today. The observation of distant objects in the universe also presents challenges. While the light from these objects is crucial to our understanding, it is often faint and can be obscured by interstellar dust and other cosmic factors. This makes it difficult to study the most distant parts of the universe. Nonetheless, advancements in telescopic technology, such as the Hubble Space Telescope and the James Webb Space Telescope, have allowed scientists to observe objects farther than ever before, pushing the limits of the observable universe and providing us with new insights into the cosmos. Ultimately, the limits of observation imposed by the speed of light and the age of the universe shape our understanding of the universe itself. The observable universe is the region of space we can study and learn about. But beyond that, we are left with questions. What lies beyond the cosmic horizon? Is the universe infinite? Or does it have some kind of boundary? These are questions that continue to challenge astronomers and cosmologists as they seek to expand our understanding of the cosmos and its fundamental nature. The observable universe is a window into the past, but the mysteries that lie beyond it remain one of the most profound and intriguing aspects of modern science. The quest to understand what lies beyond the observable universe has profound implications, both scientifically and philosophically. As we attempt to peer further into the cosmos, we encounter not only the limits of our observational tools, but also the limits of our understanding of reality itself. The very notion of an observable universe suggests that there is a boundary to what we can know, and what lies beyond that boundary challenges the very foundation of human knowledge. In this section, we will explore the significance of understanding what lies beyond the observable universe, how these scientific concepts shape our perception of existence, and how they influence our understanding of our place in the cosmos. The importance of understanding what lies beyond the observable universe can be seen in the context of one of humanity's greatest intellectual pursuits, the search for meaning and our place in the cosmos. Throughout history, human beings have sought to understand the universe in a way that connects us to something greater than ourselves. This search for knowledge is not only about discovering new facts, but about grappling with questions of existence, purpose, and the nature of reality. By understanding what lies beyond the observable universe, we not only gain insight into the structure and origins of the cosmos, but also gain a deeper understanding of our own existence. It forces us to confront the vastness of the universe and our own relative insignificance in the grand scheme of things. Yet, it also presents an opportunity for wonder and awe, as we realize that we are part of something much larger and more complex than we could ever fully comprehend. The scientific implications of understanding what lies beyond the observable universe are immense. Modern cosmology has already established that the universe is vast, complex, and ever-expanding. The discovery of dark energy and the observation of the accelerated expansion of the universe have shown that there are forces at play in the cosmos that we do not fully understand. The search for what lies beyond the observable universe is driven by our desire to uncover the deeper laws of nature and understand the true nature of reality. By studying regions beyond our observational reach, scientists hope to uncover new physics that could provide a more complete and unified theory of the universe. This could lead to breakthroughs in our understanding of fundamental forces, the nature of space-time, and the very origins of the universe itself. One of the most significant scientific implications of exploring what lies beyond the observable universe is the potential to uncover new physical laws or constants that govern those regions. The universe as we know it is governed by a set of fundamental laws, such as gravity, electromagnetism, and the strong and weak nuclear forces. However, these laws may not apply in the same way in regions beyond our observable universe. Some theories suggest that the physical constants we observe in our part of the universe could be different in other regions, leading to entirely different laws of physics. This raises the possibility of discovering entirely new realms of physics that could change our understanding of the fundamental structure of reality. The idea of a multiverse, in which multiple universes with different physical laws exist in parallel to our own, is one such concept that has emerged from the exploration of what lies beyond the observable universe. If this idea is proven to be true, it would fundamentally alter our understanding of the cosmos and our place within it. Philosophically, the search for what lies beyond the observable universe challenges our understanding of existence itself. If the universe is infinite, as some theories suggest, then the very notion of a boundary becomes meaningless. What does it mean for something to be beyond if the universe itself has no edge or limit? This concept forces us to reconsider our ideas of space, time, and the nature of reality. In an infinite universe, the idea that there is a finite limit to what we can know or observe becomes increasingly difficult to accept. If the universe stretches on indefinitely, with no edge or boundary, then our understanding of space itself must be fundamentally altered. The universe would no longer be a finite entity that we can measure and study. Instead, it would become a never-ending expanse that stretches far beyond our comprehension. The idea that the universe may be infinite also raises profound questions about the nature of time. If the universe is infinite, then time itself may not be a linear progression from the past to the future. Instead, time could be part of an eternal, cyclical process, with no true beginning or end. This challenges our conventional understanding of time as something that is constantly moving forward, and it opens up new possibilities for understanding the origins of the universe and the nature of existence. It also challenges our perception of death and the concept of an end to our lives. In an infinite universe, the idea of a final end may be an illusion, and life may be part of an ongoing process that transcends individual existence. The exploration of what lies beyond the observable universe also forces us to confront the limits of human knowledge. No matter how advanced our technology becomes, we may never be able to fully observe or understand the entire universe. The speed of light imposes a fundamental limit on our ability to explore distant regions of space, and the expansion of the universe means that some objects will forever remain beyond our reach. This realization brings us face to face with the limits of human perception and understanding. While science has made tremendous strides in our understanding of the universe, there may always be mysteries that remain hidden from us. This idea challenges our assumptions about the power of human knowledge and forces us to reconsider our place in the cosmos. Are we simply small, finite beings in a vast and indifferent universe? Or do we have a unique role to play in the grand scheme of things? In addition to the scientific and philosophical implications, the exploration of what lies beyond the observable universe also has profound ethical and existential consequences. As we learn more about the universe and our place within it, we must grapple with the responsibility that comes with this knowledge. What does it mean to understand the vastness of the cosmos if we are not capable of using this knowledge wisely? As we learn about the origins and fate of the universe, we must also consider the impact of our actions on the planet and the future of humanity. The more we learn about the universe, the more we realize how fragile our existence is and how interconnected we are with the cosmos. This knowledge could inspire a new sense of humility and responsibility, as we recognize that our actions have consequences not only for ourselves, but for the entire planet and the universe at large. Understanding what lies beyond the observable universe can also inspire a sense of awe and wonder. The idea that there are vast regions of space that remain hidden from us, filled with unknown galaxies, stars, and potentially even other forms of life, invites us to imagine the unimaginable. It reminds us that the universe is full of mysteries, and there is always more to discover. This sense of wonder is what has driven humanity's exploration of the cosmos for centuries, and it continues to fuel our curiosity and drive to understand the universe. Even if we never fully unlock the secrets of what lies beyond the observable universe, the journey itself is a testament to our desire to seek knowledge and to understand the universe in all its complexity. As we continue to explore the cosmos, we will undoubtedly encounter new scientific theories, new technologies, and new philosophical ideas that challenge our understanding of reality. The search for what lies beyond the observable universe is far from over, and it will continue to shape our perceptions of existence, our understanding of the universe, and our place within it. Whether we ever reach the limits of the observable universe or remain forever in pursuit of knowledge, the journey itself will continue to inspire and challenge us. In the end, it is not just the answers we seek, but the questions themselves that will define our exploration of the cosmos. The more we learn, the more we realize how much there is yet to discover, and that is a humbling and awe-inspiring realization. Beyond the boundaries of our observable universe lies a realm shrouded in mystery and expanse. We cannot see, touch, or measure, but one that might exist nonetheless. This region, hidden from us by the limits of light and time, invites endless speculation. Since we can only observe a finite portion of the universe, defined by how far light has traveled since the Big Bang, it's entirely possible, and even likely, that much more exists beyond what we can detect. What lies in this vast, unobservable domain? Scientists have proposed several compelling theories to explore this question, each more mind-bending than the last. One of the simplest ideas is that beyond the observable universe, the cosmos just continues more galaxies, stars, nebulae, and dark matter stretching out endlessly in every direction. In this view, our observable patch of the universe is like a tiny bubble within an immeasurably larger ocean. There may be no boundary, no edge, just more of the same cosmic scenery going on forever. This interpretation is consistent with the idea of a flat and potentially infinite universe. If the laws of physics are the same everywhere, then beyond our cosmic horizon may lie countless more regions, perhaps similar to our own, that we'll never be able to observe due to the expansion of space. But not all theories assume a uniform universe beyond our sight. Some suggest that the further we go beyond the observable universe, the stranger things might become. The laws of physics we take for granted, such as the speed of light, the strength of gravity, or the charge of the electron, might not be universal constants. Instead, they could vary from one cosmic region to another. In these scenarios, the universe is not homogeneous at the grandest scales. Instead, it might be a patchwork of pocket regions, each with its own physical rules. This idea arises naturally in some models of cosmic inflation, where different regions of space experience different conditions in the early universe, creating domains with unique properties. Even more exotic is the concept of the multiverse. This theory suggests that our universe might be just one of many, perhaps an infinite number each, existing in its own separate bubble of space-time. These bubbles could have popped into existence during a phase of eternal inflation, a process that never fully ends but continually spawns new universes in different regions. In some of these universes, the physical constants might be similar to ours, while in others, they could be drastically different. Gravity might be stronger or weaker, atoms might not form, or time itself might behave differently. These alternate universes would be completely disconnected from ours, making them forever inaccessible but theoretically plausible. Another variation of the multiverse theory comes from string theory and higher dimensional physics. According to these ideas, our universe might be one of many brains floating in a higher dimensional space, like sheets of paper stacked in an invisible dimension. Collisions or interactions between these brains might even cause big bangs, giving rise to new universes. From this perspective, what lies beyond our observable universe isn't just more space, it's a whole other layer of reality, governed by different principles and possibly home to entirely new forms of matter and energy. Scientists also consider the idea of a fractal universe. In this view, the structure of the universe might repeat itself at every scale. Just as galaxies form clusters and superclusters, those clusters might be part of even larger patterns, extending far beyond what we can see. If the universe is fractal, then beyond our cosmic horizon may lie repeated versions of what we see locally an intricate, never-ending pattern of cosmic structures. Despite the appeal of these ideas, it's important to remember that they remain speculative. We have no direct evidence for what lies beyond the observable universe, and by definition, we might never be able to gather such evidence. Yet, these theories are not just wild guesses. They are grounded in real physics and mathematics, built upon models that explain many of the things we can observe. They help us push the boundaries of understanding, even if the final answers remain out of reach. One key reason scientists believe the universe continues beyond the observable horizon is the uniformity of the cosmic microwave background radiation, the afterglow of the Big Bang. This radiation looks almost the same in every direction, suggesting that space is broadly similar no matter where you look. If the universe were finite and had an edge, or if there were wildly different regions nearby, we might expect to see signs of that in the background radiation. But we don't. This consistency supports the idea of a universe that either goes on forever or is much larger than we can currently detect. However, this same uniformity leads to another philosophical puzzle. If the universe is infinite, and matter is distributed more or less evenly, then there could be infinite variations of everything, including versions of you reading this sentence in slightly different circumstances. This isn't science fiction, it's a logical implication of infinite space combined with finite arrangements of matter. Some physicists suggest that every possible configuration of particles may exist somewhere in the infinite expanse of space, even if separated from us by distances greater than light can ever travel. Theories about what lies beyond our observable universe stretch the limits of science, but they also highlight its strength. Instead of relying on myth or mysticism, modern cosmology builds these ideas from evidence, logic, and mathematics. We may not be able to test every theory directly, but each one provides a framework for future discovery and deeper questions. By pondering what exists beyond what we can see, we push the frontier of human thought and imagination. In the end, the space beyond our cosmic horizon may hold more of the same or be completely different. It might be home to strange and beautiful variations of reality, governed by rules we have yet to discover. Or it might forever remain out of reach, a mystery that reminds us of the universe's vastness and our humble place within it. Whatever lies beyond, the quest to understand it is one of the most profound journeys we can take, not with spaceships, but with ideas. The Big Bang Theory is the prevailing scientific explanation for the origin of the universe, describing how it expanded from an extremely hot, dense state into the vast cosmos we observe today. This concept doesn't suggest an explosion in space, but rather an expansion of space itself, an event that marks the beginning of both time and the universe as we know it. According to the theory, around 13.8 billion years ago, all matter, energy, space, and even time itself were compacted into a singularity, an infinitely dense point. From this singularity, the universe began expanding, cooling as it did, eventually forming the stars, galaxies, and structures that populate the cosmos. The early universe, just moments after the Big Bang, was unimaginably hot and dense. Particles collided at extreme energies, and fundamental forces as we know them, gravity, electromagnetism, and the nuclear forces, were unified or behaved very differently than they do today. In the first fractions of a second, the universe underwent rapid changes. It cooled enough for basic particles like protons, neutrons, and electrons to form, and eventually, atoms. As time passed, these atoms came together under the force of gravity to form stars, galaxies, and larger cosmic structures. The distribution of these early elements and structures still affects the arrangement of matter we observe in the universe today. A crucial addition to the Big Bang theory is the concept of cosmic inflation. Inflation refers to a very brief period of extremely rapid expansion that occurred a tiny fraction of a second after the Big Bang, specifically from about 10^-77 to 10^-seconds after time began. During this incredibly short interval, the universe expanded exponentially, growing much faster than the speed of light. While this may sound like it violates the laws of physics, it doesn't, because it is space itself that was expanding, not objects moving through space. This inflationary period smoothed out the fabric of the cosmos and helped explain several puzzling features of the universe. One of the biggest puzzles inflation solves is the horizon problem. When we observe the universe in all directions, we see that it is remarkably uniform in temperature and density, especially when we look at the cosmic microwave background radiation, the afterglow of the Big Bang. This uniformity is strange because different regions of the universe should not have been able to exchange information or energy due to the limitations imposed by the speed of light. Yet, they look almost identical. Inflation resolves this by proposing that these regions were once much closer together before inflation stretched them apart, allowing them to reach thermal equilibrium before being pushed beyond each other's horizons. Inflation also addresses the flatness problem. Observations show that the universe is very close to geometrically flat, meaning that the rules of Euclidean geometry work on a cosmic scale. In a universe governed only by classical Big Bang expansion, such flatness would be extremely unlikely unless initial conditions were precisely tuned. Inflation naturally drives the universe toward flatness, much like how the surface of a balloon appears flatter as it is inflated. This helps explain why the observable universe appears so flat without invoking fine-tuned initial conditions. Another major consequence of inflation is the generation of tiny quantum fluctuations in the early universe. These fluctuations were stretched by inflation to cosmic scales and later became the seeds for all the large-scale structure in the universe. Small variations in density, once amplified over billions of years by gravity, led to the formation of stars, galaxies, and clusters of galaxies. The patterns of these fluctuations can still be observed today in the cosmic microwave background as slight temperature differences across the sky. These temperature differences are minute, only about 1 part in 100,000, but they provide a blueprint for the universe's development. The combination of the Big Bang theory and inflation forms the backbone of modern cosmology. It provides a coherent narrative that explains the universe's origin, early behavior, and current structure. It unites observational evidence from many different sources, including the cosmic microwave background, the large-scale distribution of galaxies, and the abundance of light elements like hydrogen and helium, which were formed during the first few minutes of the universe's existence in a process known as Big Bang nucleosynthesis. Scientists continue to test and refine these theories through observations and experiments. New telescopes and satellites, like the James Webb Space Telescope and those designed to map the cosmic microwave background with greater precision, aim to uncover deeper insights into the inflationary period, detecting direct evidence of inflation, such as specific patterns in the polarization of the cosmic microwave background caused by gravitational waves from the early universe, remains one of the most exciting goals in cosmology. Despite its successes, the inflationary model is not without challenges. Many versions of inflation predict that inflation never completely ends, but continues in different regions of space, potentially leading to the formation of a multiversine ensemble of universes, each with different physical properties. This concept, while fascinating, also introduces philosophical and scientific debates about the nature of reality and what can be observed or tested. Some physicists argue that if inflation leads to a multiverse, it may become difficult to make unique, testable predictions, potentially placing parts of the theory outside the bounds of traditional science. Still, the Big Bang and cosmic inflation remain central to our understanding of the cosmos. They provide a framework for explaining how the universe began, how it evolved, and why it looks the way it does today. They reveal that the universe had a beginning in time and that its structure and features can be traced back to processes that occurred in the first tiny fractions of a second. They also challenge us to consider questions that push the limits of human understanding: what caused the Big Bang, what triggered inflation, what lies beyond what we can observe. As our technology advances and our observations become more precise, we continue to refine our models and explore these fundamental questions. The story of the universe is still being written, but thanks to the Big Bang and cosmic inflation, we have a powerful and elegant beginning to that story, one that continues to inspire awe, curiosity, and a deeper appreciation for the mysteries of the cosmos. The concept of cosmic horizons plays a crucial role in shaping our understanding of the universe and our place within it. The cosmic horizon, often referred to as the cosmic light horizon, is the ultimate boundary that defines how far we can see into the universe. It is not a physical wall or a barrier made of matter. Instead, it is a limit set by the fundamental nature of space, time, and the speed of light. It represents the maximum distance from which light has had time to travel to us since the beginning of the universe, approximately 13.8 billion years ago. Because light takes time to travel across the immense distances of space, and because the universe itself has a finite age, there is a limit to how much of it we can observe. The cosmic light horizon exists because we can only observe light that has had enough time to reach us. Any event or object that is too far away, so far that its light has not yet had enough time to get to Earth, is simply beyond our reach. This is not due to any technological limitation, but a fundamental constraint of physics. Even if we had the most advanced instruments imaginable, we would still be unable to detect anything beyond this horizon, because the information from those regions hasn't had enough time to arrive. As a result, the observable universe is bounded by this cosmic light horizon, forming a spherical volume centered around our vantage point in space. An important factor that adds complexity to this picture is the expansion of the universe. The universe is not static, it is continuously expanding. This was first discovered by Edwin Hubble in the early 20th century, when he observed that distant galaxies are moving away from us, with more distant galaxies receding faster than closer ones. This expansion is not like objects moving through space, but rather space itself stretching, carrying galaxies with it. This means that the distance between us and other objects in the universe is increasing over time, and this expansion affects how far light can travel and what we are able to see. Because of cosmic expansion, the distance to the edge of the observable universe is not simply 13.8 billion light-years, as one might expect. Instead, due to the stretching of space, the actual radius of the observable universe is about 46.5 billion light-years. This is because as light from distant galaxies travels toward us, the space it passes through is also expanding, stretching the wavelength of the light and increasing the effective distance it must travel. This effect is known as redshift, and it is one of the key pieces of evidence for the expanding universe. The more redshifted the light, the farther away its source, and the deeper into the universe's past we are looking. The expansion of the universe means that some regions of space are receding from us faster than the speed of light. While this might sound paradoxical, it is allowed under the rules of general relativity because it is space itself that is expanding, not objects moving through space faster than light. This results in a situation where some parts of the universe are moving away from us so rapidly that their light will never reach us, no matter how much time passes. These regions are said to lie beyond the cosmic event horizon boundary, beyond which events can never affect us. This event horizon is different from the light horizon, but related in how it limits our ability to observe and interact with the universe. The concept of cosmic horizons introduces profound implications for cosmology and our understanding of reality. It implies that there are vast regions of the universe that are forever inaccessible to us, not because they don't exist, but because we will never be able to receive any information from them. The universe could be infinitely large, or it could have an exotic topology, but we will only ever be able to study the small portion within our observable horizon. Everything beyond that is hidden from us, not by choice or by technological shortfall, but by the laws of physics themselves. This understanding also shifts our perspective on what it means to observe the universe. Our observations are inherently limited to a cosmic bubble defined by time and light. We are looking at a small fraction of what might be an incomprehensibly vast universe, and yet we use this limited window to make inferences about the cosmos as a whole. This requires a combination of observation, theoretical modeling, and deep understanding of physics, as we piece together clues about regions we cannot see from the patterns and structures we can observe. The cosmic horizon is also dynamic. As time progresses, more light from distant regions will reach us, and our observable universe will grow. This gradual expansion of our cosmic view means that future generations will be able to see parts of the universe we cannot see today. However, due to the acceleration of cosmic expansion driven by a mysterious force called dark energy, there are limits to how much more we will be able to observe. Dark energy is causing the rate of expansion to increase, which means that more and more galaxies are being pushed beyond our observational reach. Eventually, distant galaxies will recede so quickly that their light will never reach us, and the observable universe will begin to shrink in terms of the number of observable galaxies, even if its physical volume continues to grow. In this way, cosmic horizons are not just boundaries of space, they are also boundaries of knowledge. They define the edge of what is knowable, what we can study, and what we can ever hope to understand about the universe. They remind us that no matter how advanced our technology becomes, we will always be limited by the fundamental structure of space-time. This limitation is both humbling and awe-inspiring. It emphasizes the fragility and uniqueness of our observational position and the precious nature of the information we are able to gather from the cosmos. As we continue to explore the universe, understanding the role of cosmic expansion and the limits it imposes will remain essential. These concepts help scientists refine their models of the universe's origin, structure, and ultimate fate. They also challenge us to think more deeply about our place in the cosmos, not as observers of the whole, but as inhabitants of a tiny island of visibility within a potentially infinite ocean of space. What lies beyond our cosmic horizon remains a mystery, one that may never be fully resolved, but it continues to drive our curiosity and our quest to understand the universe in its grandest scale. Many people imagine the universe as a massive sphere floating in space with a clear boundary or edge, beyond which lies some form of nothingness. This image, though intuitive, is deeply misleading. The universe doesn't have an edge in the conventional sense. Instead, the universe is better understood as an expanding space that either goes on infinitely or is curved in such a way that traveling in one direction far enough could eventually bring you back to where you started, similar to walking on the surface of a sphere, but in more dimensions. To truly grasp this concept, we must first challenge our everyday experiences, which are rooted in a three-dimensional world with edges, borders, and ends. The idea that the universe has no edge stems from the understanding that space itself is expanding. When we talk about the universe getting bigger, we don't mean that galaxies are flying outward into empty space like shrapnel from an explosion. Instead, it's the fabric of space itself that's stretching, carrying galaxies with it. Imagine a loaf of raisin bread baking in the oven. As the dough rises, the raisins move apart, not because they're moving through the dough, but because the dough itself is expanding. Similarly, galaxies move away from each other not because they're speeding through space, but because space itself is expanding between them. This expansion leads to a very counterintuitive realization. There's no central point of the Big Bang and no outer edge where the universe ends. Every point in the universe is expanding away from every other point. If the universe is infinite, it always has been. The Big Bang didn't occur at a single location in space, but rather everywhere at once. And if the universe is finite, then it is unbounded, meaning it wraps around itself in a way that doesn't require an edge. Either way, the concept of a hard boundary, like a wall or a cliff, marking the edge of space, simply doesn't apply. Even the notion of traveling to the end of the universe falls apart under this understanding, because the universe has no edge. There's nowhere to fall off or go beyond. Instead, you would simply keep moving through space, encountering more galaxies and cosmic structures, though at some point, The light from distant galaxies becomes redshifted so much by the expansion of space that it can no longer reach us. This limit defines our observable universe, but it's a limit to what we can see, not a limit to the universe itself. What lies beyond this horizon may be more of the same galaxies, stars, and matter. It may be something entirely different. We simply can't observe it, at least not yet. This leads to another profound idea. The universe could be infinite. An infinite universe has no edge, no boundary, and no center. It stretches out endlessly in all directions, with no repeating pattern and no final destination. This possibility is supported by observations that suggest the universe is flat, meaning it follows the rules of Euclidean geometry on large scales. In a flat universe, parallel lines never meet, and the angles of a triangle add up to 180 degrees. Current data from the cosmic microwave background radiation shows the universe is flat to within a very small margin of error. If it is truly flat, then the most natural interpretation is that it is also infinite in extent. However, the universe could also be finite, but unbounded. This means that space curves back on itself in a higher dimensional form. A two-dimensional analogy is the surface of a sphere. If you walk in a straight line in any direction on the surface of a globe, you'll never find an edge, but you will eventually return to your starting point. The surface is finite in area, yet it has no boundary. Similarly, a three-dimensional space could be curved in such a way that it loops back on itself. Such a shape is difficult to visualize because we live in three-dimensional space, but mathematical models describe this possibility clearly. Debunking the edge of the universe myth helps us better understand not just the nature of space, but our place in it. Many ancient cultures viewed the cosmos as a dome above a flat Earth, with boundaries and barriers separating the known world from the unknown. While those ideas served early human understanding, modern cosmology has replaced them with a far more complex and awe-inspiring reality, one that challenges our intuitions and stretches the limits of imagination. The universe is not a box, nor a sphere floating in empty space. It is the space itself, expanding and possibly infinite, without a border to contain it. This realization also has implications for how we interpret our observations. When we look through telescopes and see galaxies billions of light years away, we're not seeing objects near some cosmic boundary. Instead, we're seeing light that has traveled across the expanding universe for billions of years. The farther we look, the deeper into the past we gaze, and yet there's no point at which we hit a wall or a limit. We are surrounded in all directions by more space, more galaxies, and more mystery. The idea of an edgeless universe doesn't mean there are no limits to what we can observe. Our view is bounded by the cosmic light horizon, the farthest distance from which light has had time to reach us since the Big Bang. But this is an observational limit, not a physical one. Beyond that horizon may lie a universe that continues indefinitely. Or perhaps the cosmos repeats in some vast pattern, or contains regions with different physical laws, or even connects to other universes entirely. The absence of an edge is one of the most profound and liberating concepts in cosmology. It forces us to let go of everyday ideas about space and boundaries, and instead embrace a universe that may be boundless, eternal, and infinitely complex. As science progresses and we develop more powerful instruments to observe the cosmos, we may get closer to understanding the full shape and nature of the universe. But for now, the consensus remains clear. There is no edge, only horizon limits, not of space itself, but of what we can currently see and understand. The idea that our universe might be just one among many has fascinated both scientists and philosophers for decades. While it may sound like the stuff of science fiction, multiverse theories have gained traction in serious scientific circles due to breakthroughs in cosmology, quantum physics, and string theory. As our understanding of the cosmos deepens, the concept of the multiverse continues to evolve, pushing the boundaries of what we consider possible. It challenges the very notion of reality, suggesting that what we see and experience may be just a tiny fraction of an infinitely larger and more complex existence. At the heart of many multiverse theories is the notion that the universe we observe is not unique. Instead, it may be part of a vast ensemble of universes, each with its own distinct properties, laws of physics, and histories. These universes could be completely isolated from one another, or they might exist side by side in ways we cannot perceive. Depending on the theory, these parallel worlds may differ in subtle or drastic ways. Some might resemble our own, while others might be completely alien, with entirely different laws of nature. One of the most widely accepted scientific models that supports the idea of a multiverse is based on cosmic inflation. According to this theory, the universe underwent a rapid expansion shortly after the Big Bang. This inflationary period caused space itself to grow exponentially in a fraction of a second, but inflation may not have stopped everywhere at once. Instead, it might have continued in some regions while ending in others. The regions where inflation ended could have formed distinct universes, each expanding independently. This leads to the idea of a bubble multiverse, a vast cosmic foam in which each bubble represents a separate universe. In this model, our universe is just one bubble in a possibly infinite sea of other bubbles. Each bubble may contain different physical laws, constants, and structures. Some might be conducive to the formation of stars, galaxies, and life, while others might be completely inhospitable. This randomness could explain why our universe appears to be so finely tuned for life. We exist in a bubble where the conditions happen to be just right. In the vast landscape of possibilities, it's not surprising that at least one universe would have the right ingredients for life as we know it. The inflationary multiverse isn't just a theoretical curiosity. It's a natural extension of the mathematics behind inflation. The equations predict that inflation doesn't simply stop everywhere uniformly, it stops in pockets while continuing elsewhere. This leads to eternal inflation, a process that never completely ends and continually spawns new universes. These universes are causally disconnected from ours, meaning no information or matter can pass between them. They're completely sealed off, each with its own version of reality. Another powerful idea comes from quantum mechanics, particularly the many worlds interpretation. In this view, every quantum event with multiple possible outcomes actually results in all outcomes occurring, each in a separate branch of the universe. This means that every decision you make, from choosing what to eat for breakfast to deciding which career to pursue, creates a branching point where the universe splits into parallel versions. In one universe, you became a musician. In another, you pursued engineering. In one, a coin landed heads. In another, it landed tails. Every possible outcome exists somewhere in the multiverse. This branching leads to an unimaginably vast number of universes, each representing a different version of reality. Unlike the inflationary multiverse, where each universe is physically separated in space-time, the many worlds multiverse exists as a superposition of possibilities. All these parallel worlds coexist, yet they do not interact. The many worlds interpretation removes randomness from quantum mechanics. Instead of events being probabilistic, everything that can happen does happen, just not in the same universe. The idea of many worlds is both fascinating and unsettling. It suggests that there are infinite versions of you living out every conceivable scenario. While we cannot access these parallel worlds, their existence offers a potential explanation for some of the strange behaviors observed in quantum experiments. For instance, the famous double-slit experiment, where particles behave like waves until observed, might make more sense if we consider that all outcomes are occurring simultaneously in different branches of the multiverse. A third perspective on the multiverse arises from string theory and higher dimensional physics. String theory posits that the fundamental building blocks of reality are not particles, but tiny vibrating strings. To make the math work, string theory requires additional spatial dimensions beyond the familiar three. In some models, our universe exists on a three-dimensional surface, called a brane, floating in a higher dimensional space known as the bulk. Other branes may exist parallel to ours, each one potentially containing its own universe. These brain world scenarios suggest that the multiverse could be a higher dimensional structure, with each brain universe separated by a microscopic gap. While we cannot see these other brains, gravity might be able to leak between them. This leakage could explain why gravity is so much weaker than other forces. It's being diluted across multiple dimensions. In some models, collisions between brains could trigger Big Bang-like events, creating new universes. This could mean our own Big Bang was the result of such a cosmic collision. Brain-world multiverses expand our concept of space and offer intriguing insights into the origin of our universe. They also provide a potential framework for unifying gravity with quantum mechanics, something physicists have struggled to achieve for decades. Although currently speculative, these models are mathematically consistent and arise naturally from attempts to develop a theory of everything. Some thinkers have proposed an even more radical possibility, that we might be living in a simulated universe. If advanced civilizations develop the capability to run highly detailed simulations of conscious beings, the number of simulated universes could vastly outnumber the real ones. By sheer probability, it might be more likely that we are in a simulation than in the original, base-level universe. While this idea falls more into the realm of philosophy than physics, it is still discussed as part of the broader multiverse conversation. The simulation hypothesis adds another layer to our understanding of reality. If true, it raises questions about the nature of consciousness, free will, and the ultimate purpose of existence. Who or what created the simulation? Why? And can we ever find proof? While the answers remain elusive, the possibility underscores just how far-reaching and transformative multiverse thinking can be. Despite their appeal, multiverse theories face significant challenges. The biggest is the lack of direct observational evidence. By definition, other universes are beyond our observable horizon. We cannot see or interact with them, which makes testing these ideas incredibly difficult. Some scientists argue that this makes multiverse theories unscientific. They can't be falsified or confirmed by experiment. Others contend that if a theory explains known phenomena and makes accurate predictions about our universe, it's still valid science, even if parts of it are unobservable. Multiverse theories also raise profound philosophical questions. If there are infinite universes, does anything truly matter? Does free will exist if every possible decision is played out somewhere? How do we define identity in a reality where infinite versions of ourselves may exist? These questions push the boundaries of physics into the realms of metaphysics and existential inquiry. Still, multiverse models offer compelling explanations for some of the deepest puzzles in cosmology. They help address the fine-tuning problem, the fact that physical constants in our universe seem precisely calibrated to allow for the existence of life. In a multiverse, this fine-tuning isn't surprising. With countless universes, each having different properties, it's inevitable that at least one would have the right conditions for life. We just happen to live in that one. Furthermore, some versions of multiverse theory make predictions that can, in principle, be tested indirectly. For instance, bubble universe collisions might leave imprints in the cosmic microwave background radiation. Researchers have searched for such anomalies, though none have been definitively found. Advances in particle physics, gravitational wave astronomy, and cosmic background analysis may eventually yield clues about the nature of reality and the possible existence of other universes. The multiverse may also play a role in the future of human civilization. If other universes exist, could we one day travel between them? Could advanced technologies or theoretical constructs like wormholes provide a bridge? While these ideas are highly speculative and far beyond our current capabilities, they remain tantalizing possibilities in the quest to understand and explore reality at its deepest level. In conclusion, multiverse theories offer a revolutionary perspective on existence. They challenge the idea that our universe is the only one, and suggest a far grander reality, one filled with infinite possibilities, alternate histories, and other versions of ourselves. Whether these theories turn out to be true or not, they push the boundaries of science and imagination, inspiring us to rethink our place in the cosmos. They remind us that the universe, or perhaps the multiverse, is far more mysterious, complex, and awe-inspiring than we ever imagined. The cosmic microwave background radiation, often abbreviated as CMB, is one of the most significant and revealing phenomena in the field of cosmology. It serves as a cosmic relic, a faint echo of the early universe that has been traveling through space for over 13 billion years. This radiation is not visible to the naked eye, but it permeates the entire universe and holds a wealth of information about the origins and evolution of everything we see in the cosmos today. The CMB is essentially the leftover thermal radiation from the Big Bang, a kind of cosmic afterglow that provides a snapshot of the universe when it was just 380 years old. At that time, the universe had cooled enough for protons and electrons to combine into neutral hydrogen atoms, allowing light to finally travel freely through space. Before this moment, the universe was a hot, dense, and opaque plasma where photons were constantly scattered by free electrons. Once this period known as recombination occurred, the photons decoupled from matter and began their journey across the cosmos, gradually stretching into the microwave region of the electromagnetic spectrum due to the ongoing expansion of the universe. The CMB was first detected in 1965 by Arno Penzias and Robert Wilson, who were initially puzzled by the persistent noise in their radio telescope. This accidental discovery provided solid evidence for the Big Bang theory and marked a pivotal moment in our understanding of the universe's beginnings. What makes the CMB so extraordinary is that it offers a direct glimpse into the infant universe. By studying the tiny fluctuations in its temperature and polarization, scientists have been able to infer a great deal about the universe's composition, geometry, and rate of expansion. These fluctuations are not random. They represent the seeds of all current cosmic structure, including galaxies, clusters, and the vast web-like formations that span the cosmos. In essence, the CMB acts like a cosmic blueprint, mapping out the initial conditions from which all of the universe's complexity has emerged. The temperature of the CMB is remarkably uniform, about 2.725 Kelvin, with minuscule fluctuations at the level of 1 part in 100,000. These slight variations are incredibly significant because they reflect differences in density in the early universe. Regions that were slightly denser than average eventually became gravitational wells that attracted more matter, leading to the formation of stars, galaxies, and other large-scale structures. Advanced satellites, such as the Cosmic Background Explorer, COBE, the Wilkinson Microwave Anisotropy Probe WEMAP, and the Planck spacecraft have all contributed to high-resolution maps of the CMB. These missions have allowed cosmologists to make precise measurements of the universe's age, which is currently estimated at around 13.8 billion years, as well as its composition, including the proportions of dark matter, dark energy, and ordinary matter. Despite the invaluable insights the CMB provides, it also has its limitations. One of the most significant constraints is that it represents the furthest back in time we can see using electromagnetic radiation. The CMB marks the surface of last scattering, the point beyond which the universe was opaque to photons. As a result, we cannot use light to directly observe anything that happened before the CMB was emitted. This creates a kind of observational boundary that limits our view of the very early universe and anything that might lie beyond our observable limits. In this sense, the CMB acts as a cosmic horizon, a wall that restricts our ability to peer deeper into the past using conventional telescopes. Scientists have developed alternative methods to try to explore what happened before the CMB, including studying gravitational waves and neutrinos. Gravitational waves are ripples in spacetime that can travel freely through the universe, even during the epochs when it was opaque to light. If we could detect primordial gravitational waves from the earliest moments of the universe, such as those generated during cosmic inflation, it would open an entirely new window into the universe's origins. However, detecting these signals is extremely challenging and remains an ongoing area of research. Similarly, the cosmic neutrino background, which consists of neutrinos from the early universe, could provide information about conditions that predate the CMB. But like gravitational waves, these particles are incredibly difficult to detect due to their weak interactions with matter. Another limitation of the CMB lies in its resolution. While current technology has enabled us to map it with extraordinary precision, there is a fundamental limit to the detail it can provide. The fluctuations in the CMB are governed by quantum processes and random variations, which means that at a certain level, we reach a statistical limit beyond which more precise measurements won't yield additional useful information. This is sometimes referred to as cosmic variance, and it sets a hard cap on how much we can learn from the CMB alone. Additionally, foreground emissions from our own galaxy and other astrophysical sources can interfere with CMB observations, requiring complex modeling and subtraction techniques to isolate the true cosmological signal. Furthermore, the CMB does not contain direct information about the universe's structure beyond the observable limit. Because the observable universe is finite and the CMB only comes from within that boundary, we cannot use it to determine whether the universe is finite or infinite in extent, or what might lie beyond what we can see. Any structures or phenomena that exist outside our observable bubble are essentially hidden from us, not because they don't exist, but because the light or signals from them haven't had time to reach us since the beginning of the universe. This leads to fascinating but fundamentally unprovable theories about what could be beyond our cosmic horizon. Some speculate that the universe could be part of a much larger multiverse, or that it might wrap around on itself in ways we cannot yet detect. Despite these limitations, the CMB remains an essential tool in cosmology. It has helped to confirm the standard model of cosmology, known as the lambda-cold dark matter, lambda CDM model. This model posits that the universe is composed of about 68% dark energy, 27% dark matter, and only 5% ordinary matter. It also supports the idea that the universe is flat on large scales and is expanding at an accelerating rate. These conclusions would not have been possible without the detailed study of the CMB and the insights it provides into the universe's early conditions and subsequent evolution. Moreover, the CMB is helping to inform our understanding of fundamental physics. By examining its fine-scale features, scientists can test theories of quantum mechanics, general relativity, and high-energy particle physics. Any deviations from the expected patterns could signal new physics beyond the standard models. For instance, some researchers have looked for anomalies in the CMB, such as unexpected cold spots or alignments that could suggest interactions with other universes, or the presence of large-scale structures beyond our observable universe. While such claims remain speculative, they underscore the CMB's potential as a tool for probing the deepest questions about the nature of reality. In the future, scientists hope to build even more sensitive instruments to study the CMB, particularly its polarization patterns, which may contain the signature of primordial gravitational waves. If these waves can be detected, they would provide direct evidence for cosmic inflation, the brief period of exponential expansion that occurred a fraction of a second after the Big Bang. Such a discovery would revolutionize our understanding of the universe's birth and provide clues about the conditions that existed at the very beginning of time. Projects like the BICEP Array, the Simons Observatory, and the proposed Lightbird satellite are all working toward this goal, and their findings could usher in a new era of precision cosmology. In conclusion, the cosmic microwave background radiation is a cornerstone of modern cosmology. It serves as a powerful probe into the early universe, revealing crucial details about its age, composition, and structure. Although it imposes certain observational limits and leaves many questions unanswered, it also inspires the development of new technologies and theories aimed at peering even deeper into the fabric of the cosmos. The CMB reminds us that while there is much we know, there is still a vast and mysterious universe waiting to be understood, both within and beyond the limits of what we can observe. Understanding dark energy and its role in the accelerated expansion of the universe is one of the most profound challenges in modern cosmology. Since its discovery in the late 1000, 990s, dark energy has become a key player in the story of the cosmos, but its true nature remains an enigma. Dark energy is a mysterious force that permeates all of space, driving the accelerated expansion of the universe. This phenomenon was first observed when astronomers studying distant supernovae found that these exploding stars were farther away than expected, indicating that the universe's expansion was not slowing down, as had been previously assumed, but was actually speeding up. This discovery upended our understanding of cosmology and led to the realization that the majority of the universe's energy content is made up of something invisible and poorly understood. Dark energy accounts for approximately 68% of the total energy content of the universe, yet we have little direct understanding of what it is. The term dark energy was coined to describe this unknown force because, like dark matter, it cannot be directly detected by its interactions with matter or radiation. Instead, its presence is inferred by its effects on the expansion of the universe. Unlike matter, which exerts gravitational attraction, dark energy appears to have the opposite effect. It exerts a repulsive force, causing galaxies to move away from each other at an accelerating rate. This acceleration was a surprising discovery, as gravity was expected to slow the expansion over time, especially after the initial push from the Big Bang. However, dark energy's repulsive force seems to be overpowering gravity on the largest scales, and as a result, the universe is expanding at an ever-increasing pace. The most widely accepted explanation for dark energy is that it is a property of space itself. According to this view, as the universe expands, more space is created, and dark energy is thought to be associated with the energy inherent in empty space. This idea is similar to the concept of the cosmological constant, originally proposed by Albert Einstein in 1917. Einstein introduced the cosmological constant to his equations of general relativity as a way to maintain a static universe, which he believed was the prevailing model at the time. However, when it was later discovered that the universe was expanding, the cosmological constant was abandoned. It wasn't until the accelerated expansion of the universe was observed that the cosmological constant was resurrected as a possible explanation for dark energy. This version of dark energy is sometimes referred to as vacuum energy, as it is thought to arise from the quantum fluctuations of empty space. However, there are other theories that attempt to explain dark energy. One possibility is that dark energy is a manifestation of a new field, similar to the electromagnetic field, but one that affects the fabric of space-time itself. This idea is explored in the concept of quintessence, which suggests that dark energy is not a constant but rather a dynamic field that can change over time and space. Unlike the cosmological constant, which remains fixed throughout the history of the universe, quintessence could vary in strength depending on the region of space and the time in the universe's life cycle. Some models of quintessence propose that the strength of dark energy may have been weaker in the past, leading to a period of decelerating expansion, and that it has grown stronger in more recent times, driving the acceleration we see today. Despite these different hypotheses, the fundamental question of what dark energy actually is remains unresolved. Scientists are still struggling to understand its true nature, and much of the current research in cosmology is dedicated to solving this mystery. One of the key challenges in studying dark energy is that it interacts with gravity, but not with matter, in the same way that other forces, like electromagnetism, do. This makes it difficult to study directly, and its effects are only observable on the largest cosmological scales, such as the behavior of galaxies and galaxy clusters. In this sense, dark energy remains elusive, and our knowledge of it is primarily based on indirect observations. The discovery of dark energy has profound implications for the future of the universe. One of the most important consequences of dark energy is its role in determining the ultimate fate of the cosmos. Prior to the discovery of dark energy, the prevailing theory was that the universe's expansion would eventually slow down and reverse due to the gravitational pull of all the matter in the universe. This scenario, known as the Big Crunch, envisioned the universe collapsing back in on itself, with all matter and energy converging at a single point. However, with the discovery of dark energy and its role in accelerating the expansion of the universe, the Big Crunch scenario was ruled out. Instead, current theories suggest that the universe will continue expanding at an ever-increasing rate, eventually leading to a state known as the Big Freeze, or heat death. In the Big Freeze scenario, as the universe continues to expand, galaxies will move farther and farther apart, and the density of matter will decrease. Eventually, stars will burn out, and galaxies will drift away from each other, leaving behind a dark, cold, and empty universe. In this future, the universe will be filled with scattered remnants of stars, black holes, and other objects, but it will be increasingly isolated and lifeless. The exact timeline for this process is uncertain, but it is estimated that it could take tens of billions of years before the universe reaches this state. The Big Freeze is considered the most likely outcome of the universe's long-term evolution, given the current understanding of dark energy and the accelerated expansion of the cosmos. Alternatively, some theories propose that dark energy could change over time, leading to a different fate for the universe. For example, if the strength of dark energy were to increase dramatically, it could lead to a scenario known as the Big Rip. In this scenario, the expansion of the universe would accelerate to the point where even the gravitational forces holding galaxies, stars, and planets together would be overwhelmed. Eventually, all matter would be torn apart, with atoms themselves being shattered as the universe expands at an ever-accelerating pace. The Big Rip is a more speculative outcome, and it depends on the behavior of dark energy over extremely long timescales. However, it provides a fascinating possibility for the ultimate fate of the universe, one in which space itself is stretched apart to an unimaginable degree. The implications of dark energy also extend to the search for a unified theory of physics. Understanding dark energy is intimately tied to our understanding of fundamental forces and the structure of the universe. If dark energy is indeed related to the fabric of space-time, it could provide valuable clues about the nature of gravity, quantum mechanics, and the relationship between matter and energy. Dark energy is also crucial for understanding the expansion history of the universe and testing cosmological models. As researchers continue to probe its properties, they hope to uncover deeper insights into the very nature of reality itself. In recent years, astronomers have developed new techniques to measure the effects of dark energy more precisely. One of the most promising methods is the study of large-scale structure, which looks at the distribution of galaxies and galaxy clusters across the universe. By observing how these structures have evolved over time, scientists can infer the amount of dark energy in the universe and how it has influenced cosmic expansion. Another approach is the use of supernovae as standard candles to measure the rate of expansion of the universe. By comparing the brightness of distant supernovae to their expected luminosities, scientists can determine how much the universe has expanded over time and how dark energy is affecting that rate. The Dark Energy Survey, DES, which began in 2013, is one of the most significant ongoing projects in the study of dark energy. This collaboration of scientists from around the world is mapping the distribution of galaxies and galaxy clusters to study the effects of dark energy on the universe's expansion. The survey aims to measure the cosmic acceleration with unprecedented precision, using a combination of galaxy surveys, supernova observations, and weak gravitational lensing. The results from the Dark Energy Survey will help refine our understanding of dark energy and its role in the fate of the universe. In conclusion, dark energy is one of the greatest mysteries in modern science, and understanding it is crucial for our understanding of the universe as a whole. It is the driving force behind the accelerated expansion of the cosmos, and its influence on the future of the universe is profound. While we have made significant progress in studying dark energy, much remains unknown, and the search for answers continues. Dark energy challenges our understanding of the fundamental laws of physics, and offers a window into the deepest questions about the nature of space, time, and existence itself. As we continue to explore the cosmos, dark energy will remain a key focus of research, shaping our understanding of the universe and its ultimate fate. Observing distant cosmic phenomena is one of the most ambitious endeavors in modern science. As our understanding of the universe has expanded over the years, so too have our technological capabilities to explore the cosmos. However, despite remarkable advancements, the task of observing the farthest reaches of space presents significant challenges. These challenges stem from both the inherent limitations of current technology and the fundamental constraints of physics, such as the speed of light and the vast distances between us and the distant objects we wish to study. In this section, we will explore both the current capabilities and the future technologies that aim to overcome these obstacles in our quest to probe deeper into space and understand the universe on its largest scales. One of the most significant challenges in observing distant cosmic phenomena is the sheer vastness of space. The universe is unimaginably large, and even the closest galaxies and stars are separated by immense distances. For example, the nearest star to our solar system, Alpha Centauri, is about 4.37 light-years away. This means that even light, which travels at an incredible speed of about 186,282 miles per second, takes over 4 years to reach us from that star. When we look at objects further away, such as galaxies or supernovae, the light we observe today left those objects billions of years ago. This means that we are not just observing the current state of these objects, but are instead seeing them as they were in the distant past. The further we look, the further back in time we peer, and this allows us to study the universe's history, but it also means that our observations are limited to what light has been able to reach us. The speed of light is a fundamental limit that affects all astronomical observations. When we look at distant stars or galaxies, we are effectively looking back in time, and we can only see as far as light has had time to travel since the beginning of the universe. This limitation has profound implications for our understanding of the cosmos. While we can observe events that occurred billions of years ago, there are regions of the universe that remain hidden from our view, especially if they are too far away for their light to have reached us yet. This observable universe is limited by the age of the universe itself, which is approximately 13.8 billion years. Objects beyond this limit are effectively invisible to us, and we can only infer their existence through indirect methods. In addition to the distance and time limitations imposed by the speed of light, there are other observational challenges. One of the most significant of these is the interference caused by the Earth's atmosphere. Our atmosphere is full of gases and particles that can distort or block the light coming from distant celestial objects. This atmospheric interference can be particularly problematic when observing objects in certain wavelengths of light, such as ultraviolet or infrared radiation, which are absorbed or scattered by the atmosphere. To overcome these challenges, astronomers have developed a variety of techniques and technologies to observe the universe from above the Earth's atmosphere, where the interference is minimized. One of the most important technological advancements in astronomical observation has been the development of space telescopes. These telescopes are positioned above the Earth's atmosphere, where they can observe the universe in a wide range of wavelengths, including those that are absorbed by the atmosphere. The most famous example of a space telescope is the Hubble Space Telescope, which was launched in 1990 and has revolutionized our understanding of the universe. The Hubble telescope has captured stunning images of distant galaxies, nebulae, and supernovae, and it has helped refine our measurements of the expansion rate of the universe. However, despite its success, Hubble has limitations, particularly in its ability to observe the universe in the infrared and ultraviolet spectrums. To address these limitations, new space telescopes are being developed, including the James Webb Space Telescope, JWST, which is set to launch in 2021. The JWST is designed to observe the universe in the infrared portion of the spectrum, allowing it to peer through dust clouds that obscure our view of distant objects and observe the first galaxies that formed after the Big Bang. The JWST is significantly larger than Hubble, with a much more powerful mirror and a suite of advanced instruments. It will be able to observe objects that are farther away than Hubble ever could, providing new insights into the early universe and the formation of galaxies, stars, and planets. The JWST is also designed to study exoplanets and their atmospheres, providing valuable information about the potential for life elsewhere in the universe. In addition to space telescopes, ground-based observatories also play a crucial role in observing distant cosmic phenomena. While ground-based observatories are limited by the Earth's atmosphere, they are still able to capture high-quality images and data, particularly in certain wavelengths of light. The development of adaptive optics technology has been a game-changer for ground-based telescopes. Adaptive optics uses deformable mirrors to correct for the distortion caused by the atmosphere, allowing telescopes to capture images with unprecedented clarity. One of the most advanced examples of adaptive optics is the Extremely Large Telescope, ELT, which is currently under construction in Chile. The ELT will be the largest optical telescope ever built, with a mirror that measures 39 meters in diameter. Once operational, it will be able to observe distant galaxies, black holes, and other cosmic phenomena with unparalleled resolution. Another key technology that has significantly advanced our ability to observe the universe is radio astronomy. Radio waves are a type of electromagnetic radiation that can travel through the Earth's atmosphere without being absorbed, making them ideal for observing distant cosmic objects. Radio telescopes, such as the Very Large Array, VLAR, in New Mexico, are capable of capturing radio waves emitted by objects such as black holes, neutron stars, and the interstellar medium. Radio astronomy has been instrumental in our understanding of phenomena such as pulsars and quasars, and it continues to be a vital tool for studying the universe. The Square Kilometre Array, SCAR, a massive international radio telescope project currently under development in Australia and South Africa, promises to revolutionize our ability to study the universe in the radio spectrum. The SCAR will be able to map the universe in unprecedented detail, providing insights into the early universe, dark energy, and the formation of galaxies. While current technologies have allowed us to make incredible strides in observing the universe, there are still many challenges that remain. One of the biggest challenges is the sheer scale of the universe itself. Even with the most advanced telescopes, we are still limited by the vast distances between objects. For example, the nearest galaxy to the Milky Way, the Andromeda Galaxy, is over 2.5 million light-years away. Observing the entire universe is simply not possible with current technology, and it is unlikely that we will ever be able to capture a full picture of the cosmos. However, advancements in technology continue to push the boundaries of what is possible, and new telescopes and missions are being developed to observe increasingly distant objects. One promising area of future research is the study of gravitational waves, these ripples in space-time, caused by the acceleration of massive objects, such as black holes or neutron stars, were first detected in 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO. Gravitational waves provide a new way to observe the universe, allowing us to study phenomena that are invisible to traditional telescopes, such as the collision of black holes. The European Space Agency is currently developing the LISA mission, which will use space-based detectors to study gravitational waves from the mergers of supermassive black holes. This mission promises to provide new insights into the most extreme environments in the universe and could help answer some of the deepest questions about the nature of space and time. Another exciting development is the use of artificial intelligence, AI, in astronomy. AI and machine learning algorithms are being used to process the massive amounts of data generated by telescopes and observatories. These algorithms can identify patterns in the data, detect previously unknown objects, and help scientists analyze the vast quantities of information collected by modern telescopes. AI is already being used in projects such as the Dark Energy Survey, where it helps to identify galaxy clusters and supernovae. As the volume of astronomical data continues to grow, AI will play an increasingly important role in helping scientists make sense of the data and identify new phenomena. The future of space exploration and observation is incredibly exciting, with numerous missions and technologies on the horizon. In addition to the James Webb Space Telescope and the Square Kilometre Array, there are other ambitious projects that aim to explore the universe in new and innovative ways. For example, NASA's WFIRST mission, which is set to launch in the mid-2020s, will use a wide-field infrared telescope to study dark energy and exoplanets. The Chinese Space Agency is also developing its own space telescope, the Juntian Telescope, which will have a similar capability to the James Webb Space Telescope, but will focus on different areas of study, including galaxy evolution and the distribution of dark matter. In conclusion, the challenges of observing distant cosmic phenomena are vast and varied, but advancements in technology continue to push the boundaries of what is possible. From space telescopes like Hubble and James Webb to ground-based observatories and radio telescopes, we are constantly expanding our ability to explore the universe. While there are still many obstacles to overcome, the future of astronomical observation is incredibly bright. New technologies, such as gravitational wave detectors, AI algorithms, and next-generation telescopes, promise to revolutionize our understanding of the cosmos and unlock new insights into the mysteries of the universe. The next frontier of space exploration will undoubtedly lead to new discoveries that will reshape our understanding of the universe and our place within it.